In this video, we will be going over the basic properties of logarithms. In the previous video, we went over how to compute logarithms, so if you need a refresher, I will have the link to that video in the description. So let's take a look at the first property. Log base a of b plus log base a of c is equal to log base a of b times c. So this means if we have a sum of two logarithms with the same base, we can rewrite it as a single logarithm where the argument, which is the top part of the logarithm, is just the product of the two arguments, b and c, from the two separate logarithms. The second property is similar and states that log base a of b minus log base a of c is equal to log base a of b over c. This means if we have a difference of two logarithms with the same base, we can combine it into a single logarithm where the argument is just the first argument divided by the second argument. I will show you how these two properties work before coming back to the other three. So let's say we have something like log base 2 of 8 plus log base 2 of 4. Both logarithms have the same base of 2, so we can apply this property log base a of b plus log base a of c equals log base a of b times c. So this sum is just equal to log base 2 of 8 times 4, since we're multiplying the two arguments, 8 and 4, and combining that into a single logarithm. This simplifies to log base 2 of 32, which is just equal to 5, because we need to raise 2 to the power of 5 in order to result in 32. We could have also computed the two logarithms separately and then added them up. So log base 2 of 8 is equal to 3, since 2 to the power of 3 is equal to 8. And log base 2 of 4 is equal to 2, since 2 to the power of 2 is equal to 4. So this means if we sum everything up, we get log base 2 of 8 plus log base 2 of 4 is equal to 3 plus 2, which is equal to 5. So this shows log base 2 of 8 plus log base 2 of 4 is equal to log base 2 of 8 times 4, because they both equal to 5. So this is an example illustrating how the product rule of logarithms work. So here's an example to illustrate how the quotient rule of logarithms work. So if we have something like log base 2 of 32 minus log base 2 of 4, we can use this rule, log base a of b minus log base a of c is equal to log base a of b over c, and rewrite this as log base 2 of 32 over 4, since both logarithms have the same base, and it's a difference of two logarithms, so we can use this rule where the argument, the top part of the logarithm, is just the first argument divided by the second argument, so it's just 32 divided by 4. So this simplifies to log base 2 of 8, since 32 divided by 4 is equal to 8, and this is just equal to 3, since 2 to the power of 3 is equal to 8. So we could have computed both logarithms separately and then computed the difference. So log base 2 of 32 is equal to 5, since 2 to the power of 5 is equal to 32, and log base 2 of 4 is equal to 2, since 2 to the power of 2 is equal to 4. So if we compute the difference, log base 2 of 32 minus log base 2 of 4, well, we get 5 minus 2, and then that just equals 3. So this shows that log base 2 of 32 minus log base 2 of 4 is indeed equal to log base 2 of 32 over 4, since we know that they both equal 3. So here's an example of a problem type that we can solve using the product rule of logarithms. So if we have something like log base 2 of 3 plus log base 2 of 8 over 3, each individual logarithm is hard to compute. Log base 2 of 3 is hard to compute because there's no integer exponent that we can raise 2 to in order to result in 3. And same thing for log base 2 of 8 over 3. We can't raise 2 to any integer exponent to result in 8 over 3. By the way, log base 2 of 3 is between 1 and 2, because log base 2 of 2 is equal to 1, and log base 2 of 4 is equal to 2. So this means we need to raise 2 to the power of 1 point something in order to result in 3. So anyways, log base 2 of 3 and log base 2 of 8 over 3 are both hard to compute, but this problem doesn't necessarily ask for the individual values of the two logarithms. So we can actually compute this as a sum and combine the two logarithms into a single logarithm using the property log base a of b plus log base a of c is equal to log base a of b times c. So since the two logarithms have the same base of 2, we can combine the two logarithms and rewrite this as log base 2 of 3 times 8 over 3, where the argument of this logarithm is just the 3 from the first logarithm multiplied by 8 over 3 from the second logarithm. 3 times 8 over 3 is just equal to 8, so this simplifies to log base 2 of 8. And now we'll notice that we can easily compute log base 2 of 8, since we know that 2 to the power of 3 is equal to 8. So this means this logarithm is just equal to 3. In this problem type, we had a sum of logarithms where the individual logarithms were hard to compute, but once we combined it into a single logarithm, it was easy to compute, and we ended up with an integer answer. So here's an example where we need to use the quotient rule of logarithms to combine the logarithms. So if we look at the two logarithms, log base 3 of 36 and log base 3 of 4, we can see that both logarithms are hard to compute and don't have an integer value. But what we can do is we can use the quotient rule of logarithms. Log base a of b minus log base a of c is equal to log base of b over c. Since both logarithms have the same base, we can rewrite this as log base 3 of 36 over 4, where the argument of this logarithm is just the argument in the first logarithm, 36, divided by the argument in the second logarithm, 4. So now we can simplify this because 36 divided by 4 is just equal to 9. So this is just equal to log base 3 of 9. And then we'll see that this is definitely an integer value because 3 to the power of 2 is equal to 9. So log base 3 of 9 is just equal to 2. So the next property we will cover is the power rule of logarithms. Log base a of b to the power of n is equal to n times log base a of b. Basically, this is saying if the top part of the logarithm is b to the power of n, we can get rid of this exponentiation and instead bring it to the front of the expression as a constant multiple. So this is just equal to n times log base a of b, where the b no longer has any exponentiation. So here's an example where we can use the power rule of logarithms to simplify the expression. You'll notice that both log base 3 of 16 and log base 3 of 8 don't have integer values, but you'll also notice that 16 is equal to 2 to the power of 4 and 8 is equal to 2 to the power of 3. So we can rewrite the expression as log base 3 of 2 to the power of 4 divided by log base 3 of 2 to the power of 3. So we can use the power rule of logarithms and bring the exponent to the front of the expression as a constant multiple. So instead of log base 3 of 2 to the power of 4, we can rewrite this as 4 times log base 3 of 2, where the 2 no longer has any exponentiation. And we can do the same for the denominator and rewrite log base 3 of 2 to the power of 3 as 3 times log base 3 of 2. So now you'll notice both the numerator and denominator have this log base 3 of 2 term, which cancels out since both the numerator and denominator have a single factor of that term. So this is all just equal to 4 over 3. So the last two properties are fairly simple. Log base a of a is equal to 1, and this is always true. And this just means if we have a logarithm where the base is the same as the argument, it will always equal 1. And the last property is that log base a of 1 is equal to 0. And this is just saying that no matter what the base is, log base of anything to 1 is just equal to 0. And this makes sense because any number to the power of 0 is equal to 1, and therefore log base a of 1 is always equal to 0. So here are a few examples to illustrate the last two properties. If we have something like log base 3 of 3, we can see that the base and the argument are both equal to 3. So this is just equal to 1, using the property log base a of a is equal to 1. And you can see that this makes sense because 3 to the power of 1 is just equal to 3, since any number to the power of 1 is just equal to itself. So the same thing with the second example. if we have something like log base 1/2 of 1/2, this is just equal to 1 since the argument is the same as the base. For log base 2 of 1, we know that this is definitely equal to 0 because the log of anything to 1 is equal to 0. And the same thing for the last example, log base 5 of 1. That is also equal to 0 because the argument is equal to 1. So it doesn't matter what the base is, as long as the top part of the logarithm is equal to 1, the result will equal 0. Another thing to note is that the properties of logarithms apply to the common logarithm, which is a logarithm of base 10, and we just denote that as the logarithm of some number without specifying the base. So log of a plus log of b is equal to log of a times b, and this is analogous to the product rule of logarithms, except we're using the common logarithm. The quotient rule also applies to the common logarithm, so log of a minus log of b is just equal to log of a divided by b. And so does the power rule, so log of a to the power of n is just equal to n times log of a. So all of these rules involving the common logarithm are just special cases of the general rules of logarithms that we covered earlier, except this is just specific to a logarithm of base 10. So if you recall, the common logarithm is just a logarithm with base 10, so log of a is just the same as saying log base 10 of a. So here's an example illustrating the product rule of logarithms. So if we have log of 2 plus log of 5, both logarithms are hard to compute individually since they don't have integer values, but we can combine the two logarithms into a single logarithm, and we write this as log of 2 times 5 using the property log of a plus log of b is equal to log of a times b. So for the argument of this single logarithm, the 2 times 5 is just the 2 from the first logarithm multiplied by the 5 in the second logarithm. So this just simplifies to log of 10, since 2 times 5 is equal to 10, and then we know that log of 10 is just equal to 1, since 10 to the power of 1 is equal to 10. So this is just equal to 1. If we have something like log of 300 minus log of 3, we can also combine the two logarithms into a single logarithm, but we need to use the quotient rule of logarithms. Log of a minus log of b is equal to log of a divided by b, and this is because we have a minus sign in the middle, so it's a difference of two logarithms. So we can combine the two logarithms and rewrite this as log of 300 divided by 3, since we take the first argument, 300, and divide that by 3, which is from the second logarithm. Now this is just equal to log of 100, and then this is equal to 2 because 10 to the power of 2 is equal to 100, so log of 100 is equal to 2. So how about this one? This is an example where we can use the power rule of logarithms with the common logarithm to simplify the expression. So we'll notice that each logarithm in this expression is hard to compute individually because they don't have integer values, but we'll also notice that the argument in each logarithm are all powers of 2. So we can rewrite the numerator as log of 2 to the power of 3. Since 8 is equal to 2 to the power of 3, the log 2 can stay the same. And then for the denominator, log of 16 can be rewritten as log of 2 to the power of 4. And log 4 can be rewritten as log of 2 squared. So now we can use the power rule of logarithms to bring the exponent to the front of the logarithm as a constant multiple. So in the numerator, we can rewrite log of 2 to the power of 3 as 3 times log of 2. So now the 2 no longer has any exponentiation, and what we've done is we've taken the 3 and brought it to the front of the logarithm as a constant multiple. The log of 2 can stay the same, and in the denominator, log of 2 to the power of 4 is just the same as 4 log of 2, and then log of 2 to the power of 2 is just 2 log of 2. We can rewrite the numerator 3 log of 2 plus log of 2 as 4 log of 2, and 4 log of 2 plus 2 log of 2 in the denominator is just equal to 6 log of 2. So we can simplify this further and divide log of 2 from both the numerator and denominator, and we just end up with 4 over 6. We can simplify this fraction further and rewrite this as 2 over 3. So this is what this entire expression simplifies to in the end. So far, we've covered a few properties of logarithms, and there's definitely more to cover, but these are the most basic ones.